Hi, I'm Alex Wink, a meteorologist here at the National Weather Service here in Norman, and today we're going to talk to you a little bit about the equipment that we manage and the people that also manage them. It's a common misconception that we're a bunch of meteorologists within the Weather Service, when in reality, we have a bunch of administrative assistants and managers as well, but we also have a team of electronics technicians that help us maintain the equipment and keep us up and running here in the office. And we'll go through some of the equipment that we keep up with and have the people that take care of them talk to you about it. And so first we wanted to start with the ASOS network that we maintain. ASOS stands for Automated Surface Observing System. And what it is a part of our duties at the Weather Service is we produce aviation forecasts, about 24 to 36 hour surface forecasts for airports, so aviation, people flying the planes, kind of know what the weather conditions are at the surface whenever they're taking off and they're landing. And so here at the Weather Service here in Norman, we maintain 11 of these sites. And for more information on this and kind of to walk us through the equipment that we have there, we'll shoot it over to Enrique Valenzuela for more information.
Good afternoon, my name is Enrique Valenzuela. I'm an electronics technician for the National Weather Service. Right now we're here in Oklahoma City International Airport on our ASOS site. So this is our visibility sensor, visibility day and night. The way this thing works is you have a transmitter over here and a receiver. The transmitter will send a light, the receiver sees the light, and it depends on how much light it's going to see, it's going to tell you basically the visibility on nautical miles. And this is very important, especially here in the airport, because that's a good information the pilots need before they fly. This right here, this is our freezing rain sensor. This one right now is turned off because it's not a freezing weather. Later on when it starts getting cold, we come over here and we put power to the system. This little probe over here vibrates 40,000 hertz per second, and it depends on the accumulation of ice. It passes the information, and it would tell you basically how much ice we have around this area. Our next sensor is our sky condition. So this one right here uses lasers, and is shooting up basically, and it tells you, whether it's a clear sky, or in this case we have some clouds over here. So it will tell you, how far the clouds are. And then we can move to this sensor right here. This is our wind sensor. This one, you have three prompts over there. So this sensor will tell you the speed, velocity, and the speed direction. It uses sound, and depends on the sound how it moves from one prompt to the other one. That's how the system tells the direction and the speed of the wind. So we go over here to the next one. This is our present weather sensor. This one, it will tell you whether it's raining, or if there's snow, or raining ice, as well. So it can tell, actually the system it can tell the difference between one or the other. Compared to the one over there that uses light, this right here uses LEDs, and it sends information from the transmitter to the receiver, and whatever passes in between them, and the system, the system will tell whether it's, like I mentioned before, whether it's rain or ice or snow. Sometimes we have problems with this system that spider webs go in between the sensors, and the sensor is thinking that it's raining, and it communicates, with the other sensors over there, and depends on the temperature or whether that sensor over there knows that there's ice or no ice. It can tell that it's just a fault. Next, we have this sensor right here that detects your air temperature and humidity. This right here and that one on that side. And that's pretty much, this one is pretty simple. Next right here this is our water collection gauge. The way this one works, water goes into here, and this basically weights the liquid, and it tells you, by the weight, it tells you how many inches of rain or ice, is in the pocket. One thing that I would like to mention that I forgot to mention before, all these systems, they have heaters. So if it gets, to the point that it's gonna freeze, the heaters will come on. That way the sensors keep on working. And like this one over here, you have the heaters on that area. You see the little orange, or yeah, it's kind of orange, isn't it? That right there is basically your heater. Some of the problems that we also have with those heaters is that when it's really cold, birds like to go in underneath those, especially in the visibility sensor, because it's nice and warm. So we have to come over here and basically kick them out to the curb. Now all these systems over here, they communicate to this. This is the DCP, or the data collection package. This system right here provides power to all your sensors, and then all the sensors communicate back to it via fiber optic cables that go through this line over here. Then it processes all that information, and it passes that information to this, and from this antenna to the ACU that is over there in the tower on the bottom of on the base of the tower of the airport. And that's how that information gets passed from the sensors over here to the data collection package to the system over there, and then the air traffic controllers use that information to send it to the pilots, or the pilots themselves. They can tune the frequency to this system, and they can hear it themselves. Also, for us as maintainers, we can actually call the system, and we can hear the same information as the pilots hear. That way we know our equipment is working properly, or if we have any problems. And that's basically how this system works in small.
Right.
And as mentioned before, I'm an electronics technician, so this is the vehicle that we use to come to the site. We have our spare parts over here, we have our tools, and we have our test equipment. That way when we come over here, and we come over here to do, just prevent any type of maintenance, we can fix the problem, or if there's something that is about to break, we can fix it also before it breaks. So that's what we do in the National Weather Service.
Next, we'll talk about the weather radios. The weather radio in the National Weather Service is one of the primary ways that we get people in the public our messages, whether it's our forecasts or, more importantly, our watches and warnings that we issue. How that works on our end is anytime that we go through, issue a forecast, issue a watch or a warning, the software here packages it up into a weather radio message, and sends it off to our weather radio transmitters. These transmitters are positioned across our area of responsibility to make sure that everybody is covered by the weather radio broadcast. In our area of responsibility, we have 13 weather radio transmitters, and to learn a bit more about the weather radio transmitters, shoot it over to William Nardi to tell us more about it.
Hello, I'm William Nardi with the National Weather Service. My job is to service the NOAA weather radios. Right now we have 13 of them, and let's take a quick look inside one of our shelters. This is one of our more common ones. It's a Crown 300 watt. This one has a coverage of about 50 to 60 miles. It has two transmitters to give it redundancy. In case we lose one, it will automatically switch over to the secondary transmitter. Both of them are tuned to the same frequency. We maintain the same power output as balanced as we can possibly get it. Most of the system is operated through the RTC, the remote transmission controller. The audio comes in from the weather office into the back of the unit, into this, where it's split to both transmitters. Now we can listen to the input from the office right here using a speaker. So this gives us an idea in the field what's coming into it. We have other test equipment where we can actually measure the sound quality, the modulation, and see how clear it is. We also have the capability of looking at or listening to the sound going into each transmitter through the front RCA jacks. We can interface with it with a laptop through our serial port, which is kind of getting old. Hard to find a computer that has a serial port on it anymore as far as laptops go. This system has been in the Weather Service for quite a while. It's very dependable and fairly robust. Once we have finished transmitting, cleaning everything up, it comes out through a coaxial cable up to the antenna array, and from there through an omnidirectional antenna array set. There's 4 arrays up there, or 4 dipoles to be more correct. It gives us a range of 50 to 60 miles at the height of this antenna. And if you look at the topography around here, you see that it's fairly flat, so we don't have to have a 1,000-foot antenna to reach out to the area that needs to be covered. Now fortunately, weather radios are set up in such a way that we have overlapping coverage in a lot of areas. That's done so that in case this transmitter goes down hard, say we have a lightning strike on the antenna itself that burns through the antenna cable, we have other transmitters in the area that will automatically be picked up through one of the weather radios that can be purchased. All of them can be programmed with the surrounding area radios so that in case a very rare occurrence happens that the system goes down completely, people will have the emergency and standard broadcast still.
And finally, we have our weather radar. The weather radar is one of the most important tools for us forecasters here within the National Weather Service, as it allows us to be able to identify storms, be able to interrogate them, determine their structure, what hazards they're producing, and whether or not they're intensifying or not. These weather radars are really invaluable in our mission of being able to protect lives and property, as it helps us identify severe storms, any sort of winter storms, and all the hazards. These weather radars have seen a lot over the years, and to learn a little bit more about them, we'll go ahead and send it over to Monty Davis to tell us more.
Hello, I'm Monty Davis. I work for the National Weather Service in Norman, Oklahoma. This is the WSR-88D NEXRAD radar assigned to the Weather Office in Norman. The office out of Norman has 3 radars that we operate. We actually own this one. The Frederick radar, which is the Altus Air Force Base, and Vance radar, which is the Vance Air Force Base, are operated by the DoD, but we have monitored inputs from them. We also have an overlapping coverage from the Weather Forecast Office out of Tulsa. That radar we have nothing to deal with on them. However, they are a backup service for us. The 88D radar has a range of approximately 250 nautical miles. Has a power rating, we try to keep it at about a 700,000 watt output. It can go as high as 750, as low as 650,000. WSR-88D stands for Weather Surveillance Radar, D Doppler 88, 1988 model. This is the Twin Lakes radar, stationed between Lake Thunderbird to the south, Lake Stanley Draper to the west. The location that we are in here is geographically the highest location in this area. With that, let's go inside and look at some stuff. The first component we have is the radar antenna. It'd be inside the big dome here. Inside the radome, we have a 30-meter dish rotating at various RPMs at various elevations depending on what pulse repetition form the meteorologists choose to look at cloud structure at given distances. This is a medium tower, 60 feet tall, and the reason that there are antennas inside of the dome is to protect it from the weather elements, the hail, high winds, rain. It keeps dust and dirt off of it. It's a fiberglass ball, and each one of those geometric shapes is designed to withstand a force and displace the force in a given pattern so that it doesn't collapse in on itself with wind and hails. As the antenna rotates around the pedestal upstairs, it sends out a pulse, an electromagnetic pulse of energy, of microwave energy. Think of it like humming. And when you hum, you can hear your voice making waves. Well, each one of those waves would be a pulse. That pulse goes out, strikes a target, comes back. What radar does is it measures the time from the time that pulse leaves the antenna till it returns. And that will tell it how far out that target is from the antenna. After the signal returns from the target into the antenna, it's coming into the receiver system. It'll come down these pipes through a waveguide across here into this building. And in this building, it'll come into our receiver. Our receiver then filters everything through a computer processing system to where it breaks it down into its raw data and sends it to the office, and there it will create a three-dimensional model of the clouds. As I was saying, the antenna spins at various speeds at given altitude or elevations. By elevations, as the antenna is spinning, turning, it will come across at this level, move up, come across at this level, and move across. That is one volume scan. When it reaches the top, it'll come back down and start over. That data is pumped through here to the receiver where it's stored. When that whole scan is gathered, it'll send it to Norman, compile that, and then give the meteorologist the display that they see, which is a large dimensional representation of the storm or whatever they're trying to look for. This is the transmitter tube for the Doppler radar system. This is the oil bath that keeps it cool. There's actually oil that circulates in here that keeps the base of this transmitter cool as it generates RF energy. This sound that you're hearing, this pulsing sound, a real high frequency pulsing sound, are the pulses that I was talking about that it sends out and measures a return time on to give the distance to a target. So as you hear this thing pulsing like this, buzzing, in between, if you can take that buzz and spread it out over time and see in between them, that's actually turning on and off this tube. And when it's turned off, it's listening, and on, it's making a noise. That's how fast this thing is pulsing and measuring the distance and time on the target. Should we lose power to the site, this is our TPS or UPS like you'd use on a home computer. except much larger. This one uses several car batteries. There's 60 car batteries in here. And what this does is it will sense that there's a power loss from the commercial power. It'll automatically switch over. The radar will run off of this. It can run up to 5 minutes on this because the radar draws so much energy. It doesn't take it very long to drain all of these batteries. But we have a generator system over here that will kick on and take over that load. Once it's up to speed and the computer over there says that it's ready to run, it'll tell this to turn off and start recharging, and the generator over there will run the radar and recharge the generator. UPS. This radar is really, really stable. There's not a whole lot of unexpected things that go wrong with it without some form of a catalyst, loss of power, something. One thing, if you listen to what it tells you, it'll tell you when it's sick. If you pay attention to it when it's sick and help it, it'll give you a good product. There's a lot of engineering, a lot of thought that goes into this. There's a lot of attention to detail. One misstep, one instance of just losing focus on what you're doing can not only damage tens of thousands, hundreds of thousands of dollars, it can actually cost your life working on this. It can be very dangerous, but at the same time it can be very rewarding because it's never the same thing twice. The fact that the equipment that you work on is an instrumental tool in saving so many lives across the state, helping so many people in emergency situations across the state, it's extremely rewarding, and I'm so pleased to be able to work on something like this. I knew jobs like mine existed, I just never dreamt I'd ever have one.
I wanted to thank everybody for watching this video. In particular, I wanted to thank our electronic technicians and all the electronic technicians across the Weather Service for keeping us up and running. I hope you all have a great day.